Okay, so we are doing 1725 on the homework, and 17.1 is missing the speed. That's what? I don't know why. It gives you a speed, and I didn't even look it up. What's it give you, like 3,000 something?
3,380 meters.
And I don't know where this speed, they should say, well, the speed of a wave in whatever, this is going to be probably like a solid with that speed. But they must be missing that sentence, obviously, because they don't give you a speed. So then you could easily figure out then, right, the wavelength. Yeah. I don't know why that's missing. All right. So 1725, whoop. Sorry. So for 1725, we've got an ambulance moves. Okay, 1725. An ambulance moves north at 15. So I better draw my ambulance, of course. Here's my ambulance wave going this way. My ambulance is moving north, 600 hertz at rest. Okay. So this is 600 hertz. The car heads south, 20 meters per second. Here's my car. It's going this way at 20 meters per second. What frequencies are heard by the car driver? Okay, so this car driver, that's going to be a moving observer, right? This is the velocity of the observer. And we want before and after they pass. So our equation always is frequency heard of the observer is the frequency of the source times velocity over velocity. And then we always put in plus minus, and what goes up here is velocity of the observer, right? We're keeping the observer on top, and plus or minus velocity of the source. So does it give us an air temperature here? It doesn't, does it? So what are they wanting us to use for the speed of sound? Probably 340, 343. Okay, yeah. All right. Okay. So let's figure this out. We need to do before and after. Okay. So let's do before. And over here we'll do. So the frequency heard by the observer is going to be the frequency of the source, which is 600 hertz. This 343 over 343. Okay. And let's see, are they both, the ambulance is moving at 15. We're both moving here. Velocity of the source, 15. Now, let's handle this source down here first. What are both, now think of these as individual effects. If this person wasn't even moving, who cares that they're moving right now? If they weren't moving, if the ambulance is moving towards them, they should hear a higher frequency, correct? These waves are going to whack them sooner. So for the source down here then, if we want this number to go up, we want to subtract, right? So we're going to subtract the velocity of the source down here at 15. Now let's handle the observer. And let's forget about this. Let's just leave the 343 down there. We don't care right now. Just leave that at 343. Now, if the observer is moving towards the source, the observer should hear a higher frequency, right? This ear is going to enter, those waves are going to enter your ear faster, at a faster rate if you're moving towards the waves. So up here we need to add the velocity of the observer, which is 20. Now, the after is going to be now what about after they pass each other? Yeah, that's what's going to end up happening here. So if they're going past, once they pass each other, the observer's moving away from those waves, and the source is moving away. So yeah, we're going to end up with the minus, and down here we're going to end up with the plus. Oops. All right, does that take care of that? We haven't looked at this for a while on our formula sheet, but it's all here. So this is where heat starts. So we should double check. Here's heat and heat transfer methods. This in the front of your binder. So then this is a kilocalorie, so 1 small calorie equals 4.186 joules. Then we use these first equations up here, correct? Yeah, we use through here. Heat in joules. Yep.
How do I find that out? No, I mean, she knew right away that it meant heat. What defines Q as heat?
Heat is in joules. Quantity of heat in joules. This is when you want to know how much heat flows through a barrier, perhaps. And then we did a problem like how much heat flew into a cooler, like a styrofoam cooler and stuff like that. This is your heat flow or heat loss. Then, here's our equations down here. These should be all right. No, we don't really use this negative on this. Then we did elastic potential energy. We did period like this. We did frequency. And then we crossed. If we cross those, and we could fix up this correction down here. We're using, I think it's a lot easier to do the velocity. I don't know why this is a W, but velocity of sound 331 plus 0.6 times the degree Celsius does the same thing here. Plus 0.6 times the degrees Celsius. then, this is the area of a sphere. We didn't really do this last one here. Then we did the decibels. But we should put in I sub O is equal to 1 times 10 to the minus 12 watts per meter squared. That's a standard reference, right? Then we did our Doppler equation here, right? This is our Doppler equation. This is beat frequency. We'll mention that, but I don't care right now. Today we're going to do open and closed pipes. So we're going to look at this today. And that's going to get us into the lab. So last time I think I screwed up the drawing. I don't know. Well, we'll be all right. We're going to salvage this somehow. Or I'm going to start it somewhere else. This is where we left off. But let me show you. I'm just going to show you first. Here's what we're going to do, and here's what we're going to do for the lab on Friday. Or tomorrow, yes, tomorrow. Now, Carrie, hold on to that for a second, will you? Am I on the screen here? Not quite. Here. Remember, if we send a wave out on this, and I think I've demonstrated this, that I can hold this and we get a wave, correct? Now, quick review as fast as we can do it here so we don't get too bogged down. The only way to get this wave like this, where I can actually, this is interference right here. It's canceling, correct? This is my nodes right here. These are antinodes. But the only way to get that wave is this machine sends a wave out. When it bounces back from carry, it comes back underneath, right? It'd be the same way if you hit a wall with this. But it goes out, comes back. When they line up, that's where it cancels. Now, sound does the same thing. And we're going to do the speed of sound. And it's going to be this quick. If I send a wave, you got a job to do quick, Carrie, too. So we're going to calculate the speed of sound here in no time at all. So I want you to calculate. I'm going to raise and lower this. And you need to go like here at 63 minus the water height. Okay, so I'm going to send the wave down this tube. This acts like a closed pipe, but I can vary the length of the pipe because of the water level, right? So I have a closed pipe musical instrument, and my closed pipe musical instrument, I'm looking for something to whack this with, but I guess whack it with this. So you'll hear this hum. So where are we at? 57 down to 40. 42. All right. I know that that's a quarter wave. So let me show you that. This is what we're going to key on. And we're going to calculate speed of sound right there. 57 to 42, was it? Okay. Because that's my first resonant. I'll show you that. So this is vibrating at 512 times a second, right? So that's the wave I put down there. Now, you can use your phone. Your phone apps will generate a frequency. So now, I know this for a closed pipe. Here's my diagram. And this is what I was we're going to draw out. Your first resonant length, one of these waves is incoming, and one of these has bounced off, so that they are canceling at the closed end of the pipe, and this right here is your resonant sound coming out. That right there is this on our diagram that we did. If we cut the pipe right here, this is our first resonant hum length. This right here, how much is this distance if you're looking at a wave? That is 1/4 of a wave. So my wave, this right here is 1/4 of a wave. So let me concentrate on that first. So when you have a closed pipe and you can vary the length, so if that's 1/4 of a wavelength, let's vary roughly, give me a piece of, I got room. Very roughly, my frequency was, don't write this down, my frequency of my tuning fork here is 512. Okay. Let's just take 340 meters per second for the speed, and you'll measure the temperature of the water tomorrow. It'll be about the same as that. So well, your temperature of your water is going to be close to the temperature of your sound wave in there. Just a little bit. It should be very, very close to the temperature of the air here. So 340, so my wavelength should be, how do I find my wavelength? With V is equal to lambda F. Wavelength, velocity times frequency, right? So what is 340 meters per second divided by 512 hertz? What do we get? What is it? 0.664 meters, right? Divide that by 4. We get 0.166. And we were at 72 centimeters minus, what was it? 52? We were at 57 centimeters minus 42 centimeters. That's 15 centimeters. And this was 16 points. I did that wrong. This is 16.6. And we did that in 2 seconds, very crude. 1/4 of a wave that we measured was 15 centimeters. And again, we just threw that together in 2 seconds. And we should get 16.6. Okay? Now, if this would hum right here, so I could cut my pipe right here, and I'm going to get this to act as a musical instrument like you heard that hum, correct? Then the next one I could cut would be right there. Now, how much of a wave is that? That is 3/4 of a wave, isn't it? Because a full wave is to here. So this right here would be 3/4 of a wave, right? This right here is half a wave. Yep. You're not going to get any sound at a half a wave. But what is the distance between the sounds? That is a half a wavelength. So if I could hit, now for lab tomorrow, you're going to hit both of them. So 3/4 of a wave. So what is get back here. So take your calculator, somebody. 0.66 times 0.75. What is 0.66 times 0.75? So that's 50 centimeters. All right, 0.495. So 50 centimeters. So my next one should be at 50 centimeters. And I don't even know if this glass tube is... And the glass tube is only 45. But I still might hear something. I'd have to max this out, though. Yeah, I can't get it. So right here is at 1/4 of a wave?
How do you know that? Because it's the loudest?
Yes.
Okay.
Yeah, that's 1/4 of a wave right there. If I did a higher frequency here, I should be able to find the second one. Here we go. Here's 1,000. So, no, so this 1,000 is going to be half of what we just did. So instead of at, we should get one at 7.5 about. Which is going to be close to right there. So right there's the first one. That's 1/4 of a wave. Right there's the second one. That should be 3/4 of a wave. 3/4 of a wave, right? Right there. Where's my next one? A full wave and 1/4, right? So the next one would be a full wave and 1/4. So let's see if I can get the third one. 1, 3/4 of a wave. Right there. So the third length, that's 1 1/4 wave. And so on.
But this is open on the end, but so the water is making it a closed?
Yes, yes. And these work so good. Tomorrow for lab, I have closet flanges for toilets with PVC pipe that's this tall. So you're going to be able to, you're going to have one pipe way the heck up here. So it's the same setup as that for lab tomorrow. You will calculate the speed of sound tomorrow. I will be shocked if anybody's more than 3% off. You should not be more than 3% off. So yes, this acts as a variable closed pipe, right? Because of the water acts as a closed pipe. Yes, water's closing that in. What's that? Yeah, but we're changing the length. And we're still getting, it's almost like an open pipe, which we'll look at. It still bounces off the interior walls of that pipe perfectly. Hey, and if you haven't printed the lab, print the lab. So here is our next link. Since I screwed up my drawing, we'll go with this. So let's take this bottom diagram here. That has a little bit, there is a little bit of a correction factor for tomorrow's lab for the diameter of the pipe. I don't think so. So if we took this one down here, so let's look at this pattern. We know that this is 1/4 of a wave, right? How much of a wave is in this one is 3/4 of a wave. And this one right here is, this is 1 1/4 or 5/4 of a wave. Yep, 5/4, 1 1/4, 5/4.
Me and John had this discussion the other day.
What is this one? This is 7/4 of a wave. All of these go up by how much? All of these go up by 1/2 of a wave length. These go up by odd numbers. 1, 3, 5, 7. They go up by odd numbers. Those numerators go up by odd numbers. Now, if this is 1/4 of a wavelength, then this length of pipe would be 1/4 of a wavelength. Then your wavelength, if you look at it here, your wavelength for this first resonant length is 4 times whatever the length of that pipe is, right? 4 times the length of that pipe is your wavelength. So if I measured that difference that Carrie and I did in the beginning and multiplied it by 4, that would have matched our wavelength pretty darn close. Then my wavelength here is, the wavelength, we go up by odd numbers then, is 4/3 L. N is just representing going up by odd numbers. That's the frequency that you can get.
So what is the number that you're writing as 4/3?
Now this is the, I'm going to put this over 1 and then you'll see the pattern. So I have 4 times L over 1. This wavelength here is 4/3 L. This wavelength here is 4/5 L, and so on. Wavelength 7 is 4/7 L. Notice those are my odd numbers.
3, 5, 7.
Yes, N is 1357. Now, if you know the length, so N, I'm just showing you that for a closed pipe, we go up by 1, 3, 5, 7. 1, 3, 5, 7 is our pattern. The easiest way to solve this is to visualize this right here. That is by far the easiest way to solve all these problems. Now, this first one is called the fundamental. Here's just kind of the language.
4L over 1 is fundamental.
Yeah, or this, it'll say a fundamental length or a fundamental frequency, just the first one. Just the fundamental, they'll call it the fundamental frequency. But the first one is the fundamental, then the next one they'll call the first overtone. And then the second overtone, and so on. So we better do a problem. Now, hopefully not. I mean, what's a classic musical instrument where you know for sure they vary the length of the pipe? A trombone, right? Which that would be, seems like the last instrument I'd want to play, because you have to move that thing, right? You're constantly, you're varying the length, right? You're just finding where the sweet spot is in the resonant length of that trombone. So that for sure you know. No, I think your vibration of your lips is carrying the same frequency through there. Right? I would not want to play. Who's a trombone player? Anybody? Trombone? Was it easy to play? Except for vibrating the lips. What are you doing? Oh, man. Yeah. That's why I would just do a reed instrument so you didn't have to vibrate your... Okay, let's see what we got. We're going to do this problem here. 22 degrees. What length should a tube closed at one end on a day when the air temperature is 22 if its fundamental frequency is 128 hertz? So for A, first of all, let's do what What is the speed of sound at 22 degrees? You can have fundamental, they'll typically call it the fundamental frequency, or if it gives you the length. Let me solve this. 0.6 times 22.
And I did it just like that, 131.
Plus 0.6 times 22. Your calculator will do it for you.
That's right.
So, if we do that, we're going to get, what, 344? 344? All right, so we'll do 344. So we have 128 hertz. Let's see, what length tube should we use on the fundamental? We know that this is going to be 1/4, right? Yeah, I would. We need this pipe to be, if it's the fundamental, it's the first one, we want 1/4 of whatever the wavelength is. That's the way I would calculate these out. So we would use V is equal to lambda F. That is your first, the fundamental frequency is the, in this case, it's just the frequency they're using in this pipe. They're telling you that you've got to cut it off at the first.
So it's not 1/4 of the actual frequency.
It is that frequency. I don't know, because that's how they call it. So if this is 344, the frequency is 128 hertz. My wavelength comes out to be what? .672? Or no, 2.69? Yeah, 2.69, right? 344 divided by 128? What? 2.69, right?
Yes.
And if we take 1/4 of that, we're going to be at 0.672. Now, the other way to do that, no, I'm just going to teach it this way. All right, what is the frequency if you wanted to put in a fourth overtone? So the length of this pipe at the fourth overtone. So if we wanted this thing to resonate and act like a musical instrument at the fourth overtone, what frequency would we have to use? So let's go up here. So if this is the first, this would be the second, this would be the third. Our fourth overtone is going to be for what? 9. I don't know why I put an 8 there. This should be a 9. Okay. So, my wavelength, okay, 4/9 L. Now, if it wants a frequency, we can plug it into our frequency equation here, where N is, so for this thing then, N equals 9 at our fourth overtone. Yes. So if I just plug this in, F9 would be 9V over 4L. Now, it's using the same length pipe. It's the same length pipe. If we're changing the frequency. Yes, we're changing the frequency.
Couldn't we just solve for L with the number that we
You could do it that way as well. You could solve it for L. If you have a frequency though, you can use this equation pretty quick too. Because this is going to give me the frequency now, because at F9 we're going to get 9 times 344 over 4 times the same length was 0.672. So you'd have to put a different frequency into this pipe, right? You would have to change what your input frequency is. Not really, because we can change frequencies on this. So on the last one, at 128 hertz, we were only doing this much, right? At 9, we're sending this wave into that same length of pipe, and we'd have to add another one, right? At the fourth overtone, we need to increase our frequency for sure. If we want to get this many waves in that pipe, we need to increase this frequency, correct? So when we solve for this, we're now at 1151 hertz. Yes, in that same length of pipe. Okay, let's do this one down here. And then we'll go to open pipes. But let's get this closed one done here. What frequencies? Now, the fundamental and the first 2 overtones for a closed pipe. So the first 2 overtones are going to be N equals 3 and N equals 5, right? There's numerous ways to solve these. So we want the frequency. So we've got our length of pipe. So L is equal to 0.12 meters, 12 centimeters. And at 30 degrees Celsius, velocity of sound is 349. So for this closed pipe, we're trying to calculate a frequency, yes. So for this first one, what frequency do we need to get that to come up at 1/4 of a wavelength? If I'm using my equation, 1V over 4L 349. That's the fundamental frequency I could use for 1/4 of a wavelength. That is 727 hertz. Now, in my equation, if I am using the same length pipe, if I am using the same length pipe, what is going to change to get my first two overtones at n equal 3 and n equal 5? What frequencies am I going to use? That's it, right? If I change this 1 to a 3 and a 5, what happens to the frequency? We're not going to add because we're multiplying. What happens if I change this 1 here to a 3? You multiply it by 3, exactly.
So once we figure out F1, we really don't have to do that equation no more. We'll just say 727 times 3.
You got it.
7 times 5.
And 727 times 3 is 2181. Right? 2181. And F5 would be 3635. So once you figure out the fundamental, they go up by odd numbers, right? There's the fundamental, there's the first overtone, second overtone. Okay. So the next page does an open pipe. This is how they set up in an open pipe. The canceling node is in the middle. The antinodes are on the ends. This is the first resonant length fundamental. How much of a wave is in that pipe? It still sets up nodes and antinodes, so it still reflects it. Just bouncing off inside that pipe. So that's why when you said that question before, well, it's not really bouncing off in there then, is it? It's bouncing interior. They're bouncing off the inside walls of this, is what they're doing. No, amplitude is how much you're putting in there. That shouldn't change. If I have this length of pipe, I can't vary the length now. Unless I had another tube, I would kind of cheat and you'd slide another tube in and out, right? Then it would kind of work. But in this case, if I want to get this wave in there, how much of a wave is that? I would have to measure this pipe and I'd have to pick out the right frequency for this, right? Because I can't vary the length. So here's how it works with an open pipe. This open pipe is, how much is in there? This is a half a wave, right? because you can see that if you continued that, that's a half a wave. This is the fundamental. How much of a wave is in this one? This is a full wave, right? Full wave in that one? So if we look at these denominator numbers, this time they don't go up by odd numbers, they go up by ones, right? They go up by ones. So that they go up by ones, and how much of a wavelength between these? Yeah, between them. Just like last time, half a wave between them again. So we can use this equation again, but notice instead of 4L down here, it is 2L. Yes. And they go up by just ones. So in this question, what length of open pipe will have a frequency of 1200 hertz at its first overtone? That's the fundamental. Am I going to use F2 or F3 for an open pipe for the first overtone? F2. F2 for an open pipe. This would be F what for a closed? 3, right? So we are going to use F2 is equal to 2 times V over 2 times L, which we have to solve for. And I know that that's 1200 hertz. And we'd solve this for L. And they would label this L2. And L2, this 2 over 2 would cancel. So this is going to be 0.283 meters. Speed divided by your first overtone frequency. Speed divided by 2L. Oh, for the first overtone, yes. V divided by L on an open pipe. Okay, so for an open pipe, again, these numbers go up by ones. It's going to resonate when these are antinodes. These are nodes that cancel. You have to have an antinode at both ends for an open pipe. And for a closed pipe, the closed end has a node. If you have a question on beat frequencies, all you do is subtract them. So if there's a question on beat frequencies, if one of these is 343 and the other one's 340, you're going to hear 3 hertz. Beat frequencies, you just subtract. I don't know if I have a beat frequency on there. Okay, that's it for this baby. I don't know if there's a beat frequency on there. So we're going to finish up all the homework. We should. This is an open pipe here.
What's a displacement zone?
That's where they cancel. All right, see what you can do with the quiz and homework. We'll do lab. If you haven't printed out the lab, print out the lab. Did I email it to you or I just put it in Canvas? I emailed it to you. All right, yeah, print that lab out.